Alright, so we got a little introduction when we're dealing with tangent. Right? In the last video that I posted, the last video in regards to sine and cosine, you guys saw that they have a quite different structure when we're dealing with tangents and cotangents. So, right, one thing, in this video I'm going to talk about tangents and cotangents and get to this reciprocal. Because, and then in my next video, I'm going to be explaining the reciprocals of sine and cosine and how each graph is sort of connected to its reciprocal. So for instance, we know that tangent, or like tan of x, we're evaluating for this angle right here in trigonometry, we're always evaluating for a specific angle. If we say that tangent of x is equal to 1/8, for instance, right? We never know. That's too low. Let me say it's like 15/4. So we know that cotangent, or cot, right? That's how we usually say it. We say the cot of x, degrees, don't forget that, it's going to be equal to 4/15. So if you look at the pattern here, you can notice that cotangent is equal to 1/tangent of x. Sorry there, guys. Sorry there one more time. So we can see it's the reciprocal, right? So whenever we're dealing with the reciprocals for each of the trigonometric identities, we can see that the graph, or like the structure it follows, is going to be quite similar. So when we're dealing with, I give an overview for sine and cosine. So let me just give an overview for tangent and cotangent. And now we have cotangent. And then we're gonna try to graph it. So let's say we know that our amplitude is none, because this graph goes infinitely up. What changes here is like the stretch, once again, and compressing. Once again, I mean, that's not really gonna make a huge difference when we jump here to create those are real life images. And again, you don't really need this for IGCSE or something. You just really have to understand why, and this is why, right? The A is gonna equal to this. And then when we have our period, what changes now is because, see, this is our asymptote. We have our intercept, and then we have an asymptote again. Alright, so we have two major points, two major things, right? And the distance for a period is like 1 scale, 2 scale. So that's why period, and again, our first period is going to end at pi, right? Our initial period for our parent graph ends at pi for our intercept, right? Because we had that negative pi halves, and then we had 0, and then we had positive pi halves. Right, our period does not end at pi, right? Sorry there, but you can see that the period is pi, because you're adding pi's for each one, plus pi. You get for each point, you can see that the period is pi. The period isn't necessarily where the graph initially ends. It's a distance from each equivalent or each corresponding point towards the next period. Right? So, based on that, we know it's only going to be pi over b. Our x scale this time, what I was explaining, is now going to be your period halved, not divided by 4. Make that so a little bit better for y'all. Phase shift. What changes now, we have different endpoints. If you want to choose your intercept or your asymptote, right? But your function changes. So function changes. It depends on your endpoints, right? You can either have negative pi halves or a pi halves as your asymptote, or you can have 0 and pi. And again, this is not for cotangent. For cotangent, it's going to change a bit. So let's just say this is for tangent. I'm just going to focus on tangent for this video, right? Let's just focus on tangent for this video. Cotangent, I'm going to be doing in my next one. But what I want you guys to see between tangent and cotangent is that the period, the way the period is formed is going to be the same. The way the x scale is formed is going to be the same. The amplitude is going to be the same. What changes is basically your phase shift and your vertical translation It's still D. It's going to be the same. Right? I want to look at some practical examples. But you guys should really just look back on how to do these if you forgot it, because I don't want to be too repetitive. Right? So remember, if we have like y equals tangent of 2x. You know, this is going to change. You know that this is still 1. And remember, what this one is going to do, if it's greater than, if your a is greater than what we say 0, we usually tend to have a horizontal compression. But if a is smaller than 0, we tend to have a horizontal stretch. So you can really see if your graph is going to look fattier or skinnier. Stretched, right? But in this example that I've given, we're not really dealing with that. What we're actually dealing with is, well, you know, the amplitude doesn't change. You go infinitely up, infinitely down. Next thing you look at is your period, right? And our B is 2. If we get 2, I'm sorry, if we do, so our period's going to be pi halves, right? Our phase shift is still going to look at 0. So it's still going to start at 0. No, it's not, because we're doing the tangent, right? So, no. So what we do is the 2x. If we do the intercept, or we can do the asymptote. If we do the asymptote, we're probably going to have to start there. So if I just do the intercept, and I know that equals 0, right? So I can divide, yeah. So basically my starting point will still, my starting intercept will be here. But of course, if I do my asymptote, it's going to be my following point. And then I can add a period. I can add pi halves. Then find again my next intercept. And basically this cycle goes on and on and on and on and on and on forever. So it's sort of an infinite process. But I would rather you guys starting at your, if you do the endpoint at equals negative pi halves, that'll be better, because then you have your asymptote, and you can go from asymptote to your intercept, and then from your intercept to your asymptote, and then from your asymptote to your intercept, and then from your intercept back to the asymptote, and then from asymptote back to your intercept. Right? So that's why, because it's not going to make sense if you have this, this, and this, because this is not a complete period. Two complete periods, as I said, is always going to have is this, 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 and this. This is 2 periods. Right? You can start this way so that you can easily find the next 2, but I would rather start using the asymptote. So do your endpoint negative pi halves. So f of x can equal this, and then f of x for your end. This is your start, and this is your end. That can be pi halves. Right. So let me just show you guys some technology now. So jumping here now, as you can see here, we have tangent of x, right? So you can see this is sort of the shape that I previously mentioned before. So you have that curving point, and then you have the parabola going infinitely. You can see it's going infinitely up, and then you have one going infinitely down, right? But look how interesting this can get. If we add, for example, let's do 2 pi. My graph it's shifted. You can't really see, but it's going to be shifted, right? There's sort of a shift. Like, pay close attention since you guys are, right? It gets shifted. But now, what I want you guys to see is just the d, how interesting the d can get, and a little difficult at first. So plus 2, you can see, oh, Guilherme, it still looks the same, but it doesn't. Look at the turning point, the curve. It's shifted 2 units up, because we have 2 here. Our d is 2, so we shifted 2 units up. And lastly, this is 1, once again, right? Whenever we don't have a number, it's always because it's being multiplied by 1. But if I do 9, look what happens to the graph. You can't even, I mean, let's even put that 0 there. So we go, it's very skinny, horizontally. But look what happens if we have, for example, 0.5. Let's do 0.8. It gets way fatter horizontally. You can see that it's fatter. Right, and this is all because of trigonometry uses. Thank you all. Guilherme de Castro.